I have been super busy with work recently, and part of that is because I got myself a new tool, which is Carbide 3D's Shapeoko, and that uses a hybrid table clamping mechanism, which has aluminum tracks and also MDF spoil board. And they provide these with the system. I really love that they provide a lot of the clamps, hold downs. It really seems like their idea is they want you to get the thing and immediately succeed with it. So they want to give you at least the basics to get started. And I think that's a really cool way of approaching it. But back to this part. So I believe it's a glass-filled nylon, and it's designed for injection molding. You can see this cut back here and another cut here so that your wall thicknesses are about even all around the part. With injection molded parts, if you have different size walls, then it can cause shrinkage differences, and that can cause problems. So often with injection molding, they carefully control your wall thicknesses. And also with injection molding, because it's shot all at once, then you have more isotropic properties within the part. On their website, which they do provide this design so that you can print it out if you want. They have a whole library of different things that you can go ahead and print out on a 3D printer. They say that this doesn't work amazingly as a 3D printed part, and of course not as well as their glass nylon part. And that's probably true, especially because this was not designed to print. So one of the things that I want to do in this video is I want to speed run you through doing a fully parametric design for a replacement for this that's functionally essentially identical, but very, very sturdy, robust, and works well on the table. Similar performance to this part right here. So I want to talk about that. I also want to share a few other things about the particular setup for the Shapeoko in case it helps you. So I was also looking for inexpensive alternatives to their Teez-Nutz. They are a great design. They work wonderfully. If you like those, buy a bunch of them, right? And the fact that they have this thread that sticks up, that's really nice. But I was looking for other cheap options, and I had a different hold down requirement that I was looking at things other than M6. And so in that search process, I found these. This one happens to also be M6. I had to use some M5 ones, which is what started me down this path. And then I realized, oh, I could also buy some M6 of those and use them and replace the Teez-Nutz entirely if I want to. So these are readily available in large quantities, and they're normally used on this kind of a thing. Very similar geometry into the hold down pattern, but they're very, very short, which is a problem. And it would be a huge problem if we didn't have 3D printers and the ability to design stuff. So I made this little part, which will also be posted the link in the video description. Check it out and you'll be able to find more details about both the fusion design, which is going to be fully parametric for this guy, and then just the step file for this guy so you can easily print it out. Call this the nut supporter, and this can be printed out of anything. This one's printed out of PETG, and it just pops in there like that. If you want, you can glue it, and then this just slides in your track. You're able to put your PLA printed part in, and then you slide your screw in. It, like I said, it's M6 as well, and crank stuff down, and you can print out as many as you want. And these things are normally sold in hundreds. So there's a through hole here so that doesn't present any challenges for you. So anyway, all of that to say, this provides some alternatives for the CNC router if you happen to have a Shapeoko table or a similar sort of table and you're interested in any of these. You'll be able to get those designs free, so check out the link in the video description. Also, for guys who don't have that and are just interested, we're going to go through a parametric design for this part in Fusion right now. So here we go. So over to Fusion 360. Since we're going to do this as a fully parametric part, the first thing to do is to go into the parameters area of Fusion 360. And then you just click the little plus sign and add your parameter. You use your name, make sure the units are set to what you want, and then type in your expression. That expression doesn't necessarily have to be a number. It could also be an equation, and we'll use that later. I'm going to go through and do a whole bunch of these. So before designing this part, I did what I really like to do is I took out a piece of paper and a pencil, and I sketched out the whole part, the whole design. I measured the whole part, and got all that down on the piece of paper, made sure it made sense, and that was my starting sketch, which I'm going to copy all those numbers off of in order to fill out this whole parametric document. So I'm just copying off that list and getting part by part each variable down and filled in. Now, one of the interesting ones, of course, is yes, you can do your units as millimeters, but also degrees. And so make sure that your units are correct, and you can mix and match. You can do inches and millimeters in the same design. And I'm just going to take advantage of the snipping tool to take a copy of that so I remember what the names are, because somewhere in the middle of my design, I'll forget what I named something. So moving on. The next thing that matters is figuring out how you want to orient your part so that either it works in an assembly, or in this case, when you download this file and go to drop it on your build plate, it's going to start in the orientation towards the build plate that I want it to, right? And initially I was going to make it go to the left here, but my sketch is to the right, so we're just going to scrap that and do the sketch to the right. So I'm just laying out the rough shape. I'm not worried about sizes yet. We're going to dimension it here in a second, but I'm just laying out the rough shape for it. And this is roughly the shape of my clip, and we'll start by dimensioning it and then typing in the variable name, and it will show f of x, as you see there, and then the actual real dimension, which is a good way of knowing that that is a parameter, and that is what that parameter is evaluating to. So we're just going to pull this thing in and make it roughly the correct shape. Fill up this little gap in the front. Now it's turned blue. We know that it is a closed shape, so that can be extruded and turned into a solid part. And all I'm doing is going through here, dropping the dimensioning tool, typing in the variable name, using my snipping tool cheat sheet to remind myself when I forget, and then just clicking what it's dimensioning across. As you dimension these in, you'll see that they go from blue to white to show you that they're constrained. Some of them have constraints for when I drop them in that are horizontal or vertical. And so you have horizontal or vertical, you have the starting point, and then you have the length of that segment, and then that leads to a fully constrained part. And there's just a couple parts here that are missing constraints. I've got that little foot, and then this thing needs an angle. And all of those are variable names that I've already written in. So all the variables look good. We're going to go ahead and finish the sketch. Now we're going to click on that closed space, and we're going to pull it out. And I want to do something different here because I'd like the center line to be the center plane. But the problem is that my dimension is the total depth. So what I'm going to do is just use the total depth divided by 2, and then the symmetric part thing will make it all work out correctly. So I like to take some time in between steps to just carefully look over the part, make sure it all makes sense. I'm just thinking through how it looks, and I'm thinking about adding the fillets on the corners here. But generally that's best to do last. So I decided not to do that. We're just going to scrap that and go ahead and place the cutout on the top of the part. So first thing I'm doing is creating a center line. I click the line, click X. That makes it a construction line so that it won't try to extrude later. We're going to set these two equal to each other, and then we're going to connect them with some geometry. We need to make sure that that's done properly and that all of the points are tied up. So first thing we're going to do is make sure that it's tangent, so that the line is on the outer edge of the circle. So every one of these is tangent. And it's the bottom left one's not showing that it's tangent because that's an implied, I guess, constraint. So it would be redundant. But just to be sure, I'm just grabbing it and moving it around, which is a good thing to do. If you're not sure that things are properly attached, grab and wiggle your part, and if things are not attached, it'll be obvious really quickly. So I'm going to clip out these inner elements, because what we want is an overall kind of a oval shape. When you dimension off of a curve, normally it takes the center radius, and I don't want to do that. So what I'm going to do is I'm going to add this line here and apply it tangentially to that curve, right? And I've made it a construction line by clicking on it, hitting X, and that now allows me to grab that line and dimension that to where I want. And so that's the dimension that I actually want to grab. I don't want to also subtract out the radius of that part, which you can. You can go into the parameters thing and you can make functions inside the parameters. Just for the sake of simplicity though, I'm doing it this way. And I'm just doing the same thing over here, is setting up another line, setting it tangent, making it a construction line, and then I can use that line to measure off the edge and set that equal to my variable that I've already set up. So there we have our dimensions. The one that we're missing, though, is this groove diameter. So we'll select the groove diameter, and there's our sketch. And then we're going to grab the extrude. Because that is a dotted line, it doesn't interfere with the extrude. Otherwise, you might have to click multiple places to get the whole feature. But because it was a construction line, construction lines don't interfere with those. So now we have this groove, which looks oddly large, but we'll come back to that later. In the meantime, though, we'll go ahead with the fillet and do the corners. And we do have a variable for that as well. So we're going to select all the corners that we want and then type in our variable. And it's always a good idea to grab your part, look around, and make sure you didn't miss anything, because that happens. So everything's in there. I'm just going to go up in here and going to change this to my function. And that means I don't have to go back into that feature to make changes. I can just go into the parameters section and change that parameter. So now we have our curves, and this doesn't look right, and here's the answer. It says radius, right? So what we're going to do is we're type that divided by 2. So we're putting in the diameter divided by 2, and it's seeing that as the radius. Now we have the feature behaving in the way that we expected it to, the way we wanted to. So no wonder why that looked a little funny and large at the time. So, but going back into the parameter section, we can select any parameter that we want and just make a change, and it cascades into the part. That's what a fully parametric part is. And the beauty of this is when you download this file, if you download the native SolidWorks file, you don't even have to do a remix. You just import the SolidWorks file, you pull up parameters, you change the number that you want, and you can redesign this part to have a longer clamp radius or be taller or take a larger or smaller bolt. Whatever it is that you want to do for your specific design. This is one step beyond showing you how to do remixes. This is making a part that is basically ready to remix. All you have to do is type in numbers. So that's really cool. And so if you're designing parts and putting them up there, especially parts like this that make sense that people would want to modify them, help everybody out, and don't just place the step file, which is way better than the STL, but also export it as a Fusion file and make it a fully parametric part so that anybody can get this part, grab onto it, change the features, and away you go. I'm going to chamfer this side as well, just a little bit, just to break that edge. I'm not going to do it in the center where the bolt rides, to make sure that it gets as much clamping area as possible. And then, yeah, just playing with these dimensions. You can. The nice thing about this is you can fiddle with it and say, maybe I want a bigger foot, and I don't like the way that looks, or this is perfect. So this is all it takes. Is you go into the parameters area, change a number, and it changes how everything looks. It's a really cool feature in pretty much all of the 3D design software that I'm aware of. But this is how you do it in Fusion. So we're just going to save off the part. Should have started with saving the part, really. So we're going to save that. We're going to export it, and then pull it over into the slicer, and then we can get into some detail about the the slicer. So one of the things that I want you to think about is that 3D printed parts have a grain direction just like wood. So wood needs to be oriented in a certain way for maximum strength. The exact same is true with 3D printed parts. And so to maximize the strength of this particular part, when I introduce it into the slicer, I'm going to introduce it on its back so that you don't have any overhangs or any parts like that, and then all of your grain is lying flat with the bed. So when this thing is laying flat on its back and it's clamped, it'll basically be in compression. Now, you can slice apart, and in order to save material, you use hollow infill like this. And for many parts, that's plenty strong. And for this part, that may be strong enough. That's something that you can play with in the slicer once you get the part in here. However, because I want this part to be as strong as possible, I'm going to make it a solid infill. But I'm not just going to quote-unquote make it solid infill. I'm going to go in here, make them rectilinear. I've had certain cases where rectilinear, because it's crossing patterns, was actually stronger than a concentric all walls sort of design. So that's worth considering in certain part configurations. So we have the walls, pretty thick walls, which will give us really good support, especially on that bolt. And then we have a little bit of rectilinear infill so that every layer switches directions. And especially if you have a bending moment, that can make a stronger part than just regular walls. Also, material selection matters, so I would not use PETG for this kind of a in-load application. It might be okay because this is a short-term load application, but PETG tends to bend and yield and stretch. PLA is great unless you're having heat issues, in which case you might want to look at ABS or another material. So regardless of whether you came here for the Fusion parametric design, or you are also somebody with a CNC router table and were interested in the hold down tips, I hope that you got value out of this video and enjoyed it. Because it's fully parametric, this design can be changed if you want to make it longer, if you want to change the hold down characteristics, if you want to change the foot, you just go in there, change the numbers in the design. You don't have to redo the design. If you want to change from an M6 to a 1/4-20 or anything else, you can change that slot size. And these little nuts are available in 1/4-20 as well, not just M6. So look around, check your dimensions. There's definitely options there. So I hope that you found this video useful, and I appreciate your time. Thank you very much. Anyway, I'll call this... Anyway, button head, I believe it's a 25mm long M6 screw. So in normal usage, you get something like this. Now the advantage of this design is that your button head is below the surface of your hold down, and so you're less likely to accidentally catch it with a bit and break a bit. And that's a good thing and a great design feature, design goal, etc. What I did, though, in my part, because I'm starting to learn how to design toolpaths in Fusion, what I did is I've just changed my retract height, and so that hasn't been a problem. So that wasn't as big of a concern for me. So for the 3D printed part, I printed this out of PLA. So there is some consideration for when you design a part for 3D printing, you want to think about what material you want to print it and what orientation you want to print it. For folks here who are more familiar with woodworking, 3D printed parts, just like woodworking, are where grain direction matters. So if you cut a small piece out of the wood in one direction, the grain will just split because of the grain direction is weak in that orientation. Same thing happens with 3D printing. You will have weaker stuff. So if you printed this standing up and your layer lines were along here, sorry, I got a black background here, so I'm trying to put it somewhere that's not my face. There we go. If you printed it this way and then you load it in this direction, it's much more likely to snap off, right? So this was designed to be printed flat. Sorry, I keep getting it in the black background. This was designed to be printed flat so that the layers stack on top of each other and you almost get everything in compression. The other thing is I generally use it with a washer. And so that spreads the load, and you don't have as much of a point load. You're less likely, you get more spreading of the load across the surface area of the part. Okay. Also, material matters. So I printed this out of PLA, not PETG. PETG does have better temperature characteristics in general, but it's also just a little bit bendy. And so it's generally not the best. So for this, where it's a short-term work holding thing, it would probably be fine, but for longer term load bearing things, generally it's not the best design. So I actually saw a video of Katz Moses making these clamps that were supposed to go on the wall out of PETG, and PETG isn't the best material to be used for that application. But I hope it works out for him. Anyhow, so the other thing is I was looking for alternatives, very cheap alternatives, to their Teez-Nutz. They are nice, they're great, and if you want to buy those, you absolutely should. However, there are other options out there. I found this, which this is normally used in an aluminum track like this. So you slide it in here. If you recall, I said it was M6. The Teez-Nutz are, let's just start that over.